Hi, welcome to the second video in series of Learn C++. So I thought about it and I think it makes sense if we go back to the very beginning as how this all started. Why did we even need a programming language? So computer systems are created using a lot of gates and electronic circuits, which I'm going to talk in a little bit. So let's just have an understanding of how this circuit works, how a programming language was used to get some useful work done using these electronic circuits. So I'm going to just talk about some electronic basics, which is going to be very helpful for a programmer. So talking about logic gates, what are logic gates? We have a combination of many gates that we can create using the basic logic gates, but these are the very basic logic gates we have. The first one is buffer gate, which will buffer input. If their input is 0, which means 0 volts, it will just output 0. And if the input is 1, which is 5 volts in this case, the output will be 1. Similarly, for the AND gate, this is a truth table. Truth table kind of gives you the output given a given input. So in this case, for AND gate, if the input is 0 volts and 0 volts on both input pins, the output pin will give 0 volts. Similarly, if we have 0 volts on in A and 5 volts on B, the output will be 0. So think of AND gate as kind of a multiplication. So 0 multiply 1 is 0, 1 multiplied by 0 is 0, and 1 multiplied 1 is 1. So in this case, AND gate, if the input on A is 5 volts and the input on B is 5 volts, the output will be 5 volts. We have OR gate, uh, which will give output of 1 in case any of the inputs on A and B is 1 or 5 volts. We have XOR gate, which will kind of only will give output of 1 if there is the input on A or B is different. For example, if A has 0 volts and B has 1 volts, 5 volts, the output will be 5 volts and vice versa. And we have inverted gate, which will just invert the input. If the input is 0, it will give 1. If the input is 1, it will give 0. And similarly, we have NAND gate, which is combination of AND gate and NOT gate. So it will give the output of AND gate, but it will inverse the output. And NOR, which is combination of OR gate and NOT gate. And so gates is a way to understand the digital circuits. It's all part of the digital circuit. The way they are implemented underneath is using the transistors. Transistor is kind of a very basic element of electronic circuit. You have emitter base collector. In this case, the first diagram is showing that how OR gate is created. We have two inputs A and B, and we have output. And if the base is excited and you give some voltage on the base of this transistor, it gives the output. In this case, if any of the A or B is excited, so the transistor will pass through the voltage that's given at its input, and the output will be 1. And if you look at the AND gate example, it will only output 1 if both of them are excited. For example, if B is 0, so even though A is 1, because B is in series to A, it won't give output as 1. Only if both of them are 1, only then it will give an output of 1. So this diagram is just to kind of show that how internally gates are implemented. They are implemented using transistors, and we have like uh, millions of gates that are implemented in a CPU that finally executes all the instructions that we give the computer to execute. Going back to a simple example of a full adder using gates. So this example is just to demonstrate that how a simple addition is done for two numbers. In this case, we are not even adding two numbers, we're just adding 2 bits. So this is a logical circuit for adder, full adder, which takes in input A and B, which is just one bit at a time, and then carry, and it sums it up using this gates that we discussed. In this case, we have OR gate and AND gate, as, and it gives output sum and carry output. If you look at the truth table for this one, you look at that. So if carry is 0, A and B is 0, sum is 0, carry is 0. And if A is 1 and B and carry N is 0, the sum is 1 and carry is 0. And finally, in the end, if you look at it, if carry is 1, A and B are 1, then we have a sum of 1 and carry output is 1. So the reason I gave this example is so that you can visualize how numbers are added within a electronic circuit. So what happens underneath a chip is that you have this combination of gates that are added, and your instructions that you give to the CPU or to a microcontroller or any chip, you kind of toggling the input to this inputs, whether it's 0 and 1, and depending upon the instruction that you execute, you get the output. And even though this looks a little complicated, but in a chip or in microcontroller or in a CPU, you have like millions of these ones that are executing your instructions that you added as in form of assembly language or any programming language. So I'm going to spend some time talking a little bit about the internal architecture of CPU, but it's at a very basic level. There's a lot going on within a CPU, and you can find all the material online if you are interested as how CPU works. But on a very high level, you have a bus that carries the instructions and the data. You have a RAM, which is a random access memory. So everything that is executed by a CPU fetches us from RAM. CPU internally has caches where it will store the instructions as well as data for some time before it's executed. Those are very fast. So we have L1 cache and L2 cache, but those are very fast memories, but at the same time very expensive. So we have this random access memory, which is comparatively faster than the hard disk, but is slower than caches. So you write a program, it's stored in a RAM. Even the data that you are referring to in your program is stored in a RAM. And using the buses, CPU fetches those instructions. And CPU has this concept of called program counter, which is like a pointer that is pointing to the next instruction that will be executed by the CPU. And you have a timer. So when you say that, okay, my CPU is 2 gigahertz, what does that mean? So that means that you have the CPU has internal timer, and whenever CPU gets a tick, it fetches the next instruction and executes it. Uh, so while that clock is going on, CPU can execute as many instructions as the clock of the CPU. The main component of the CPU that executes your instructions is the ALU, or arithmetic logic unit. So you have a instruction register which contains instruction that needs to be executed, and then this is decoded and finally sent to the ALU for execution. ALU will execute an instruction and will store the result in an accumulator, and which is written back to the RAM for output. So when this all started, the code was written in form of assembly language. So there was some sort of instructions that were exposed by the CPU manufacturers, and you will use those instructions to create a very simple programs like adding two numbers or creating a subroutine and storing that and calling that subroutine, giving it some arguments. So CPU has this registers where you can load some data that you want a CPU to refer to, and then finally execute the instructions and store the result in accumulator where you can fetch it and get the results from. So this is a very simple program in assembly that just prints hello world. The idea is that so that you are a little familiar as how CPU is doing everything underneath. We have section.data where all the constant data is stored. In this case, we are storing the string hello world, which is terminated by the end character. And then we have string length, which is like address of this line and then minus the address of string, which will kind of give you the uh, length of this hello world string. And then we have a section dot text. Dot data section contains all the constants and the data that your program refers to, and then the dot text section contains your code that the CPU will finally execute. In this case, we are loading the syswrite function code, which is 4 in this case, into the register EAX. CPU has these registers that are available for you to use for writing a code. In this case, we have EAX, EBX, ECX, EDX. These are the 4 registers that we're using. So think of this as like calling a function by giving the arguments, and you're telling the CPU which function to call. In this case, you're telling CPU, okay, I'm interested in syswrite function, which is like code 4. You're loading it in EAX, and then you specify that what is the where you want that output to go. And in this case, you're saying standard out, which is the screen, computer screen. So you're saying 1. And in ECX, you're loading the address of the string, which is hello world here. And then EDX, you're loading the string length so that CPU knows how many characters it needs to output to that uh, to console. And then you're finally calling interrupt ATH. A little bit about interrupt, how this works. So something, interrupt is a signal to the CPU so that it will stop whatever it is doing, and then it calls the interrupt service routine, which is which is kind of a handler for that interrupt. In this case, we are calling interrupt ATH. So there is some routine that is written somewhere in the software that CPU will call, which will send all the arguments that you passed here, and that routine will execute and then finally return. Once it returns, CPU will resume whatever it was doing before. So in this case, as I already mentioned, that we have a program counter, which is the current instruction that CPU is executing. So whenever it gets an interrupt, it will save that PC on the stack, and then will call your interrupt service routine, giving all the arguments. And then once that interrupt service routine is executed, it will resume the execution by popping the address from the stack, the program counter in this case. And finally, here in the program, we are calling the system exit function code with the return code 0 and calling interrupt ATH, so which is interrupt kernel to perform system call. So this is how basically it's done. So the idea is not to scare you with this like arcane language here. The idea is that you should be familiar as how things are done by the CPU. Now, where the high-level programming languages like C and C++ come in picture is that you have a compiler, and you have a compiler, assembler, and then linker. You write code in very easy to understand language, in easy to understand logic, and finally the compiler changes that code into here's a diagram for that one. So the compiler changes that code into the assembly code, which then assemblers convert it into object code. And finally, a linker will take that object code and use the libraries that it needs to use. Uh, Libraries in this case could be any system libraries or a standard C++ library or any third-party library that somebody wrote, and finally creates a binary that can execute on the CPU and do whatever you want to do. So there's a whole lot going on when once you write a code and then is executed by the CPU. But most of these things you don't have to worry about, but it's good to understand how things are done in the back. Um, I think this is mostly I wanted to discuss today. So as I promised, I'm gonna create next video where I'll be talking about how to prepare your system to write some very simple programs. We're going to start with installing the compiler and then making sure that our system is ready for us to work. Um, I'll recommend downloading VS Code, which is a very nice IDE with syntax highlighting and the autocomplete features, I will be using that, but you're free to use any, and even VI is good enough for now. So if you need any more information about all this, just write me a comment below and subscribe to my channel. Thank you.